Introduction. Hello students, let us have a look at our first chapter, that is electrostatics. After studying this chapter, you will be able to explain Coulomb's law, electric field and Gauss's law, define superposition theorem, describe electrical potential energy and electrical potential, understand the concept of capacitors, explain direct current, understand the concept of dielectric polarization, define Van de Graaff generators. We will first try to understand what is electrostatic field. An electrostatic field is an electric field produced by static electric charges. The charges are static in the sense of charge amount. It is constant in time and their positions in space. Charges are not moving relatively to each other. Electrostatic field plays an important role in modern design of electromagnetic devices whenever a strong electric field appears. Coulomb's law, electric field and Gauss's law. Coulomb's law explains the electrostatic force between two point charges at certain distance in free space. French physicist Coulomb constructed a device for the precise measurement of the interaction forces between electric charges. The electrostatic force between two point charges is proportional to the amount of electrostatic charge on each of them and proportional to 1 over the square of their distance. The proportionality constant K depends on the unit system used and in the S12 interpretation. An electric field surrounds electrically charged particles and time-varying magnetic fields. The electric field depicts the surrounding force of an electrically charged particle exerted on other electrically charged objects. The concept of an electric field was introduced by Michael Faraday. The force appears only due to the existence of electric charges on both geometric objects. This means that around each electric charge, the space has special tense condition that is observable through the force existence. This special feature, or so to speak, behavior of the space around electric charges, is called the electrostatic field, or simpler, the electric field. The force acting on the charge Q1 appears due to the electric field of charge Q2 at the position of charge Q1. The force acting on the charge Q1 appears due to the electric field of charge Q2 at the position of charge Q1. Mathematically written, it looks as, according to equation 1.3, the electric field around any point electric charge has the form where Q is the charge, RQ is the position vector of point charge and epsilon 0 is the dielectric constant or electric permittivity of a vacuum. Gauss's law, also known as Gauss's flux theorem, is a law relating the distribution of electric charge to the resulting electric field. Gauss's law has a close mathematical similarity with a number of laws in other areas of physics, such as Gauss's law for magnetism and Gauss's law for gravity. In fact, any inverse square law can be formulated in a way similar to Gauss's law. Electric fields and conductors. In this video, you will be able to charge an electric field of a hollow conductor. Look at Wimshurst's machine with hollow conducting sphere and an electroscope for measuring the charge on conductor. For this purpose, we also use charge scoop and conducting balls. When we rotate the wheel of Wimshurst's machine, the charge is conducted to the sphere. Now touch the scoop with sphere and charge transferred from different parts of sphere to scoop. When we touch the scoop to electroscope and the needle of electroscope shows fluctuation. Let now developing the charge in the sphere by rotating the wheel and transfers the charge from inside of the sphere to the scoop and touch it to electroscope. Now needle of electroscope shows fluctuation again. Finally, we observe the effect of the electric field on the distribution of charge between two balls. For this, we develop the charge on sphere and it conducts to first scoop and then first to second. When we touch second scoop to electroscope, it shows fluctuation through their needle and first scoop shows no fluctuation. Electric fields. In this video, you will be able to know electric field patterns around charges. In this experiment, we used castor oil, which has a high insulating property, some electrodes for conduction of current, a petri dish, some semolina seeds for polarized the induction of electric field, and a high voltage power supply unit. Both the electrode dipped in castor oil and semolina seeds containing petri dish and switch on the power supply at high voltage. Now the semolina seeds are sprinkled into the oil. They will around and orientated the electric field lines. In this case, the electric field lines simulating between the two charges. This diagram represents the electric field lines between the point charges and arrow shows the displacement of unit charge from positive to negative. Now two different types of electrode placed in the oil and simulate the electric field line around the isolated charge. The diagram shows the electric field pattern produced by 1 point positive charge. Finally, simulate the electric field lines between the two parallel plates and the seed sprinkled due to electric field and show parallel line between the two electrode plates. This diagram represents the electric field pattern between the two elongated plates. Superposition theorem. The superposition theorem for electrical circuits states that for a linear system, the response, voltage or current in any branch of a bilateral linear circuit having more than one independent source equals the algebraic sum of the responses caused by each independent source acting alone, while all other independent sources are replaced by their internal impedances. Let's now understand the superposition theory through an experiment. Here you can see two power supplies 6 volt and 12 volt connected in a circuit. Circuit contains three resistances: R1 100, R2 270 and R3 220 ohm. Set the first power supply unit at 6 volt and second at 12 volt. Multimeter is used to measure the voltage. Now measure the voltage across R2 resistance and connect the millimeter to it and we measure the voltage. Electrical potential energy. Electric potential energy or electrostatic potential energy is a potential energy measured in joules that result from conservative Coulomb forces and is associated with the configuration of a particular set of point charges within a defined system. An object may have electric potential energy by virtue of two key elements: its own electric charge and its relative position to other electrically charged objects. This moving charge follows the general definition of work and changes the potential energy. Energy stored between two charges shown by equation of electric potential energy, which is similar to the equation of force. Electric potential energy also similar to gravitational potential energy. Capacitors. A capacitor is a passive two-terminal electrical component used to store energy in an electric field. The forms of practical capacitors vary widely, but all contain at least two electrical conductors separated by a dielectric insulator. One plate of the capacitor contains negative and other positive charges. Electrons enter through the negative plate of the capacitor and they repel the electron of other sides. Dielectric polarization. To understand the polarization of dielectrics in the electric field, we take a dielectric slit which contains molecular dipoles. When applied an external electric field of it, the negative poles of the molecules move in the direction of electric field, and finally all the molecules get aligned. In this situation, left surface of the dielectric substance shows negative and right surface shows positive, and in the center of the substance there are aligned positive and negative charge. The electric flux density is less in right side as compared to left side. Here, external electric field is equal to the electric field, and inside electric field is equal to electric field minus polarization of the electric field. This phenomena is called as dielectric polarization. Van de Graaff generators. Van de Graaff generator is used to generate high potential differences of near about million volts. Then the generated potential differences are used to speed up the particles like ions, etc. A simple Van de Graaff generator consists of a belt of silk or a similar flexible dielectric material running over two metal pulleys, one of which is surrounded by a hollow metal sphere. On the front panel, it contains two controllers, first for on and off control and second for speed control. Inside of the generator, there are few parts like motor, resistor, speed controller and power switch. Electricity comes into the power cord and runs through on and off switch and speed controller. Resistor is used for up and down the speed of motor. When switch makes on, the motor runs. A third wire is connected to motor and the case of panel. It is ground wire and attaches the device to the ground because earth is the greatest reservoir of charge. As the belt passes in front of the lower cone, it receives negative charge that escapes from its points due to the influence of the electric field around the lower pulley, which ionizes the air at the points. When switch is on, the charge is transferred from lower pulley to the upper pulley of sphere through the belt.